Algebra 1, Lesson 64, we are looking at inverse variation, being able to identify it, write an equation, and graph it. So it's very similar to direct variation. Remember that direct variation has an equation of y equals kx, where we're saying every time we multiply by a constant in order to get the y. To find the constant, we use a quotient. Well, we use a quotient of y divided by x. So to find the constant, we use a quotient, and we use a product in the equation. Inverse variation is just the opposite. The constant is found by using a product, and the equation uses a quotient in order to find the relationship. The big thing is that the relationship between the two variables is a constant product. So looking at these, we have our two equations at the top, and we're going to fill in this chart in order to find all the ways you can make a rectangle having an area of 16. And I have a width and length of 1 and 16. We could also have 2 and 8, 4 and 4, 8 and 2, and 16 and 1. What we notice is all of these have a constant product of 16. We have x times y always equaling 16. And the other thing is that as we increase the x, the y decreases. So as we increase the width, so going 1 to 16, we see that it decreases the length. Okay, these are opposite operations. I should have drawn it kind of like that. Basically, as one goes up, the other goes down. Or as one goes down, the other goes up. That's inverse variation. So when we have the constant product, we can say if x times y equals 16, then I can write an equation by saying y equals the constant divided by x. So, direct variation has y equaling the product of k and x, whereas inverse has y equal to the quotient of the constant and x. So let's determine if the next few relationships are inverse or if they're direct. So in this case, y divided by 6 is equal to x. Well, in order to decide, we need to get y alone. So in this case, we need to multiply by 6 on each side. And we get y is equal to 6x. Well, since this is a product between the constant and the x, this is direct variation. All right, once again, let's get y alone, and by doing that, we're going to divide by x, and so we get y is equal to 5 divided by x. This is a quotient of the constant and x, so this is inverse. For this one, it's going to take a couple steps. We want to get y by itself, and we currently have x is equal to 36 divided by y. Well, we don't really want y in the denominator, so I'm going to multiply by y on each side. And we have xy is equal to 36. Well, that first gives us a clue because we have a product of our two variables giving us a constant. Another clue is when we solve for y, we get y is equal to the quotient of the constant and x. And last one, we're going to multiply by 12. And we get y is equal to 12x. So in the middle one here, we get inverse variation because it's a quotient of the constant and x. In the second one, it's direct because it's the product of the constant and x. We have this product rule for inverse variation, which helps us when we're given some of the information but not all of it. What we're saying is if we're given a point, x1 and y1, and another one, x2 and y2, then if we multiply together x1 times y1, that has to equal x2 and y2. Because anytime we take an x times a y in our inverse variation, they have to have that constant product. So let's say we're given the information that if y varies inversely with x, and y equals 3 when x equals 12, basically they're giving us this coordinate point of 12, 3, find x when y is 9. So we don't know x, but we know y is 9. Well, what this is saying is we can set up an equation by saying x1 times y1 needs to equal x1 times, or x2 times y2. Well, all we need to do is solve for x. And 12 times 3 is 36, so if we have 9x equaling 36, x must equal 4, because we need to have that constant product. 12 times 3 equals 36, 4 times 9 equals 36. This is how we figure it out. Okay, so here are the steps listed out again. All right, so let's try it again. Y varies inversely as x, and we have that x is 12 when y is 5, but we don't know x when y is 3. So it looks like our constant product, when I multiply these together, I get 60. That needs to equal 3 times something, 3 times my x. So it looks like x has to be 20 in order to keep that constant product. Okay, so just plug it in. We say x1 times y1, 12 times 5 equals x times 3. All right, write an inverse variation relating x and y if y is 8 and x is 3. What we're saying is we know that this is inverse variation. So what we can do is say, I really just need to find the constant. So we say our constant in inverse variation is found by multiplying together x and y. So we do that. 3 times 8. So if k is 24, we can substitute it into the inverse equation by saying y is equal to the constant 24 divided by x. So we can use this to create a table of values. We can say, what if we plug in -6? Well, we get -4. Divide by -4 there, we get -6. -2 gives me -12. 0, if we divide by 0, we get undefined. We can't divide by 0. 2, we get 12. 4, we get 6. 6, we get 4. And we can plot these on a graph. If we do that, I'm just going to quickly graph these. 6, -4, -4, -6, -2, -12 would be about down here. And I'm going to put another one on here. We're going to put -12, 2 would also be another solution. And so we can start to see this is definitely not linear. It's actually a curve. Now I draw it like that because it's never going to touch this line right here. Where we have 0, x as 0, this is undefined. We show that with a dotted line. What that dotted line means is that my curve, no matter how far down this curve goes, it's going to get closer and closer and closer to 0, to x equals 0, but it's never going to touch. Because we can continue to take x and put in different x values, but regardless, we can get closer and closer to putting in x as 0, so x as -1.5, -1, -0.5, -0.25, closer and closer and closer to 0, but we're never going to touch 0 because it's undefined. We're going to look at the other side of this curve. Let's see, we have 2, 12 would be up here about. We have 4, 6. We have 6, 4. And I'm going to add another one, 12, 2. And so we have my curve. Same idea here. No matter how close I get to this 0, x equals 0, if I have a half, a fourth, an eighth, a 16th, no matter how close I get with x and dividing by that x, I'll get closer and closer to that line, x equals 0 or y equals 0, but I will never touch it. What this line is called, it has a funny name, it's called an asymptote. A-S-Y-M-P-T-O-T-E, an asymptote. What this is telling me is that I'm going to get closer and closer to this line, but I'll never touch it. Another asymptote that we have on here is actually on the other axis. So we have one as y equals 0, but we also have x equals 0. Or sorry, I just switched that. We have x equals 0, that's our vertical line, and then we have y equals 0. What this is saying is that if we have y equals 0, 0 equals 24 divided by x. Regardless of how big or small we make x, we could never take 24, divide it by something, and get 0. We could get close by going higher and higher and higher in the x's, or lower and lower in the x's, way out here in the hundreds, millions, thousands, but we will never divide 24 by anything big enough that it will actually equal 0. So we get closer and closer and closer, but we will never touch this horizontal line. It's called an asymptote right there. So similarly, let's do another one. If I have y equals 6 and x equals 2, that means that my k, my constant, is 12 by multiplying those together. So my equation is y equals 12 divided by x. So that when I fill these in, 12 divided by negative 6 is negative 2. We get negative 3. We get negative 6. 0 is still undefined. Okay. We plug in 2 and we get 6, 3, and 2. So we plot these and we get, well, negative 6, negative 2, negative 4, negative 3, negative 2, negative 6. So we're going to have this curve. And then we're going to have a very similar one in the first quadrant. 2, 6, 4, 3, and 6, 2. So very similar curve. And of course we have lots more options. You can see that the x values that I've picked in order to graph this equation, they're all factors of my constant. Both positive and negative factors of my constant. It helps me to be able to decide where my curve is. Now once again, I have asymptotes at x equals 0, and I have an asymptote at y equals 0. Okay, so this is how we graph our inverse functions. Pick x values that are factors of your constant and then just plug them in. Right now, while we're doing these simpler inverse variation equations, that 0, plug that in as well, just to remind you that it is undefined. So here's a word problem example. I'll just read it to you, and it'll be very similar to what we've done already. A truck driver's speed is inversely related to her travel time. If she is traveling at 55 miles per hour, it takes her 13 hours. How long will it take her if she goes 65 miles an hour? So let's say x is my time, so 13, and y is the speed, 55. Well, we don't know how long it takes for this 65 miles per hour, but we can plug it into our equation to say 13 times 55 is equal to some x times 65. And all we have to do is solve for x. We'll get that constant and figure out, well, it has to be constant, so I have to find a factor multiplied by 65 that will give me that same constant. Similar idea here. Sally's riding her bike at a rate of 12 miles per hour. It takes her an hour and 3/4 to get to the concert. How long would it take her if she goes 18 miles per hour? Well, we have a coordinate point, 1.75 hours for 12 miles per hour, and we have a certain amount of time for 18 miles per hour. So I'll get 1.75 times 12 is going to equal x times 18. Those products have to be the same. Well, 1.75 times 12, that gives me 21. So 21 equals 18x, so I divide by 18, and I see that it's going to take me 1 1/6 hours if I were to go 18 miles per hour. 1 1/6 hours to go 18 miles per hour. I just reduced that and put it into a mixed fraction. Well, I hope this is helpful for your homework and for studying.